All right, we're talking about dehydration reactions. A dehydration reaction, right, means you're removing water. You're going to remove H and OH. You remove OH from one, H from another. Whether it's a double bond, you move OH from one side, H from the other side. Or there's two compounds coming together. You move OH from one, H from another. That's dehydration. We remove water because water is a very stable product. So you want an equation showing the dehydration reaction produce diethyl ether. Ether just has an oxygen in the center of it. Okay. So this is diethyl ether right here. We haven't gone into ethers yet, but ethers just have an oxygen with two R groups. Have we done ethers yet? I don't think we've done ethers yet with naming them. All right. But an ether is just simply R-O-R. That's an ether. Okay. So we have ethanol. Ethanol, everybody should be familiar with ethanol, is CH3, CH2OH. Two of those combine. And it tells you it's a dehydration reaction. Let me make sure it's being, I think I set the recording. Yeah, it's being recorded. Perfect. Okay. So it tells you it's a dehydration reaction. It means you're removing an OH from one and an H from the other. Okay. So this one, we're removing OH. This, we're going to remove the H. And we're going to connect right where that came from. So you end up with CH3, CH2, and there's an O. This section right here. Okay. And it connects to the CH2, CH3, which is this compound right here, diethyl ether plus water. And that's a dehydration reaction. So the dehydration reaction of an alcohol is going to produce an ether. Okay. And we'll have different ones in a little bit going at different examples where in the next chapter or so we'll have different results because you have different alcohols rather than the same one. But it's the same exact principle. Okay. Dehydration reaction between two molecules of 2-propanol. Propanol is CH3. There's 3 carbons, right? On the number 2 carbon, we have an OH group. CH3. Okay. So you have 2 molecules of that. And again, dehydration tells you you're going to remove OH from one and H from another. That's your water molecule. So we have 2 of these molecules of 2-propanol. Okay, we remove OH from one and H from another. So this oxygen is going to attach right to that carbon you lost the OH group. Okay, that's a dehydration reaction. Here's your 2 compounds. Okay, we're removing OH and H. And this oxygen is going to attach right to where that OH group was left off. Okay. And this is an isopropyl group. Okay, so it's di-isopropyl ether. Okay. All right, any questions? That's where we left off last time. We finished that up and we left off right here, medical use of ethers. Okay, so any questions so far? We all good? All right.
Yeah.
All right, perfect, thanks. So ethers are often used as anesthetics. Okay, they accumulate in the lipid material of nerve cells and they interfere with the nerve impulse transmission. So they stop the nerve from transmitting its impulse. So therefore the muscles can't contract, the patient can't move. Okay, and it's an anesthetic, like a general anesthetic. Okay, today halogenated ethers, okay, are used routinely as general anesthetics. Halogenated ethers are ethers with halogen, bromine, chlorine, fluorine, iodine, attached to the R group of the ether. Okay? And that's used as general anesthetics. They're less flammable if they're halogenated. Okay, they're safer to store and to work with because they're less flammable. Okay, so this is diethyl ether. We made it from two molecules of ethyl alcohol or ethanol. This was the first successful general anesthetic in the 1800s. Was diethyl ether. Okay, because again, it accumulates in the lipid of the cell and it prevents the nerve from carrying out the impulse. This is a halogenated ether. You can see here's your R group. Here's your R group. And we have fluorine attached, chlorine attached, fluorine attached, chlorine attached. So it's a halogenated ether. It's a lot less flammable. It's a lot safer to work with. Okay, and it's called penthrane. We'll try to name those in just a little bit according to IUPAC. That's just its trade name. So why do ethers have much lower boiling points than alcohols? Alcohols are ROH, ethers are ROR. What does an alcohol have by looking at its formula there that an ether does not have?
Hydrogen bonding.
Perfect. Exactly right. Alcohols have hydrogen bonding. Hydrogen bonding occurs when the hydrogen is directly attached to a small electronegative element like oxygen, nitrogen, or fluorine. So if hydrogen is directly attached to the oxygen, you're going to have hydrogen bonding. You don't have that with ethers. You have hydrogen, you have oxygens, but the hydrogen is not directly attached to the oxygen. The carbons are. Okay, so you do not have hydrogen bonding. So ethers have a much lower boiling point than alcohols. Alcohols are going to have a much higher boiling point because the hydrogen bonding holds those molecules together. Okay, ethers don't have hydrogen bonding, whereas alcohols do. Hydrogen bonding creates greater intermolecular forces. Remember, intermolecular is between molecules, okay, which determines a substance boiling point. When something boils, it breaks apart. Okay, those molecules break apart from each other. So the more force holding it together, the higher the boiling point. That's why hydrogen bonding creates a higher boiling point in alcohols than you have in ethers. Okay. Describe the structure of ether molecules. We just said that. We have a hydrocarbon group bonded to an oxygen, bonded to another hydrocarbon group. And it could be this could be the same, or that could be R prime, that could be different. Okay, could be two methyl groups, could be a methyl group and an ethyl group, could be a methyl group and a propyl group. Whatever, they don't have to be the same. They can be the same, they don't have to be. So the ether has two R groups bonded to a central oxygen atom. The R groups can be the same or different, and they're usually hydrocarbons. Okay. Thiols are compounds containing a sulfur, an SH bond. Instead of the alcohol, which is ROH, now you have thiols, which is SH. So instead of the oxygen, you have a sulfur group. That's a thiol. They have the formula RSH. Okay, they're similar in structure to alcohols, with the S replacing the oxygen. And if you look on the periodic table, everybody remembers the periodic table, right? The big funny thing with all the elements on it. Okay, directly below that, directly below oxygen is sulfur, which means it's in the same family, which means it has the same chemical properties, the same number of valence electrons, same chemical reactivity. So it reacts the same as oxygen. Disulfides, okay, have the formula RSSR, okay, where the hydrogens have been removed and you have a sulfur bridge between the two, which is common in supporting certain proteins. It helps get proteins tertiary structures, which we'll go into coming up. The R group may be aliphatic, which is a hydrocarbon, or aromatic, which is a hydrocarbon benzene ring. Okay, remember, aromatic compounds are the benzene rings, and aliphatic is every other hydrocarbon. Okay, so benzene rings have their own type of chemistry because of that conjugated double bond system which makes them extremely stable. Okay, the name is based on the longest carbon chain, and you put the suffix thiol at the end, and the position indicated by the number. You put the number where the SH group is. So it's the same thing as alcohols, except in putting OL, you put THIOL. So instead of OL, it's thiol at the end. But the same rules apply as naming alcohols. Okay, so here we have the longest carbon chain. Okay, you give your functional group the lowest possible number as always. So 1, 2, 3, 4. So we got a methyl group at number 3, and we got a thiol group at number 1, and we got 4. A length of the longest carbon chain is 4. And it's all single bonds, so it's butane. So instead of butanol, it'll be butanethiol. Okay, 3 methyl, 1 butanethiol. Okay. So there's our group. So there's our 3 methyl group that tells us there's a methyl group attached to the 3rd carbon. Number 1 tells us where the thiol group is, the SH, and there's 4 carbons all in a single bond. So it's butanethiol. Okay, so instead of dropping the E and adding OL, we keep the E and add thiol to the end. But it's the same exact thing as alcohols. We just change the suffix. Okay, thiols, a lot of thiols are scents, they smell. Thiols, as many other sulfur compounds containing compounds, have a nauseating aroma. They do not smell good. Okay, rotten eggs is the smell of sulfur. We add that smell of sulfur to natural gas. Natural gas is odorless. Okay, we add sulfur to it, thiols, to make it smell. So if there's a leak, we can smell the leak. That's why we do it. But natural gas has no smell. Okay, it's completely neutral. But we add something to it to make it smell in case it does leak. Okay, so thiols do not smell good. This, when a skunk uses its spray, those are thiols. It gets your attention real quick. Okay, defensive spray of North American striped skunk is a thiol. Onions and garlic, the smell from those are thiols. They're a sulfur hydrogen group. They have a distinctive aroma to them. Okay, so here's the different thiols, different smells you can have. You have trans. Again, if it's trans, you know that the carbon groups or the alkyl groups are on opposite sides of double bonds. Or the hydrogen groups are on opposite sides of double bond, but it's on the different sides of the double bond. Same side is cis, opposite side is trans. This is butene because there's a double bond, so it's E and E, 4 carbons with a double bond at the number 2 position, and number 1 carbon is a thiol group, SH. So there's your thiol group right there. Okay. Look at the top right. Again, 4 carbons. Here's your number 1 because that's where your functional group is attached. There's number 2, number 3, and number 4. So again, it's 1 butane thiol. At the number 1 carbon, there's a thiol group, and it's butane, 4 carbons, all single bonds. And at the 3rd carbon, there's a methyl group. So 3 methyl, 1 butane, thiol. Again, same way we named alcohols, except in alcohols, we drop the E, add OL. In thiols, we keep the E and add thiol for the sulfur containing group. Okay. And this is the alcohol compartment of it here. This is an alcohol. Okay, we name it by dropping the E and adding OL. So 2-phenyl ethanol. So ethanol has 2 carbons. The functional group is always number 1. So we have ethanol. Okay, that's your OH group. 2 carbons, and on the 2nd carbon we have a phenyl attached. Remember, if it's a benzene ring with an OH group, it's phenol. If it's a benzene ring that attaches to another carbon, okay, it's phenyl. That's how we name the substituent. Do not get phenol and phenol mixed up. Phenol is attachment, phenol is an alcohol. Okay. Okay, the next one on the bottom left here, you can see it's octadiene, 1-ol at the end. Remember, we work backwards in chemistry. So 1-ol means there's an OH group at the number 1 carbon. Octadiene means 8 carbons, 2 double bonds. Octa is 8, di is 2, ene is your double bonds. So the double bond at number 2 and number 6. Oops, how to go backwards? Oops, I didn't go back, so I went forward. There we go. We're back. All right, so at 2 and 6, there's a double bond, 8 carbon chain long. And at 3 and 7, there's a CH3 group. Those are your methyl groups. Okay, those are smells of, those are sweet smells. Those are nice smells. They're smells like roses. The thiol ones are smells like a skunk scent. So alcohols usually have a pleasant smell. The thiol groups have a very nauseating smell. Okay, so naming these thiols, the IUPAC name for the following thiols. Okay, so how many carbons do we have here?
2.
Perfect. We have a 2 carbon chain. So this is ethane. And what do we add because of the SH group here? Thiol. Ethane thiol. That's the name of it. It's at the number 1 carbon, and no matter if either side it has to be the number 1 carbon, so it's the same thing. I flip it up around. So there's only one compound that can hatch. You don't put a number in there. Okay, so ethane thiol. If you put ethane 1-thiol, it would not be marked wrong. Okay, it's just redundant. You just don't have to put it in there for this one. But if you did put it in, I would not mark that wrong. Okay, let me get rid of some of those words then now. Okay, this one here, 2 carbons again. Okay, so ethane and 1,2 dithiol. Okay, so 1,2 ethane dithiol. Here you have to put the numbers. Why?
There's more than one.
Perfect. There's more than one choice you can have. Because if you can have carbon, here's your 2 carbons, you have your SH group here, and I can have an SH group here. That's 1,1 ethane dithiol. This is 1,2 ethane dithiol. So because you have 2 groups here, it could be both on the number 1 carbon, or it could be one on the number 1, one on the number 2. Okay, so see the difference? So here, if you did not put the 1,2, I would mark it wrong. Because you have 2 different compounds you could possibly have an ethane dithiol. So you have to tell me which one it is. Okay, so that has to have the numbers. And it's 1,2 ethane dithiol. You have thiol groups, there's 2 of them at the number 1, number 2 carbon, and there's 2 carbon longs in the carbon chain, and it is all single bonds, A and E. So all your information is right there in the name. Okay, there's a fun one. Let's do the longest carbon chain, happens to be this chain right here. Are we going to number that chain from left to right or right to left?
Right to left.
Perfect, right to left. Because our functional group, the thiol group in this case, always gets the lowest possible number. So 1, 2, 3, 4. So 4 carbons is butane, all single bonds. At the number 1 position, we have a thiol group. At the number 3 position, we have a methyl group. Okay, so 3 methyl, 1 butane thiol. 3-methyl 1-butane thiol. It's the exact same thing we do with alcohols. There's no different, except in alcohols, we drop the E and add OL. In sulfur groups, thiols, we keep the E on the end of the name and we just add thiol. But it's the same exact logic as going through the nomenclature. The same thing. So don't get confused just because it's a thiol group. All right. So again, we got the longest carbon chain. Now on this one, are we going to number left to right or right to left?
Right to left.
We're still going to number right. We're still going to name right to left. Okay. Because it went from the left, the first thiol group is number 2. If we go from the right, the first thiol group is number 1. And we always give the functional group the lowest possible number. So we got 1, 2, 3, 4, 5 carbons. And we have 2 attachments. Okay, so we have pentane, 5 carbons, all single bonds. And we have 2 SH groups, so 2 thiol groups. So it's 1, 4, pentane dithiol. Okay, so 1, 4, pentane dithiol. There's 2 thiol groups, and there are at numbers 1 and 4. Okay, it's pentanes, your 5-carbon chain. A and E is all single bonds. Okay, so everything in the name has a purpose, has a reason, and it tells you exactly what the structure is. So don't get confused in naming thiols. We've done it all before, and just exact same thing as alcohols. It's nothing different. Draw the structure of each thiol. 1,3-butane dithiol. Okay, you should all be able to do that. Remember, I told you to work backwards. Okay, thiol means SH group. Dithiol means 2 SH groups. So butane is 4 carbons. Now I'm going to do the line structure. 1, 2, 3, 4 carbons. That's butane. Okay, and numbers 1 and at number 3. There are 2 thiol groups. So 1,3-butane dithiol. Okay, and there it is written out in the structural formula. 4 carbons, 2 SH groups, thiol groups, 1 at number 1, 1 at number 3. Okay. 2-methyl, 2-pentane thiol. So let's go back, work backwards again. We have 1 thiol group and we have pentane. Pentane is how many carbons? 5 carbons. Perfect. Let's do the like line structures. 1, 2, 3, 4, 5 carbons. Okay, there's your pentane. There's a thiol group at number 2. So let's pick this as number 2. And there's our thiol group. Okay. And at number 2, I have a methyl group. So I draw a line right here also. Okay. So there's my methyl group, there's my SH group. So 2-methyl, 2-pentane thiol. You want to see it written out? Okay. Number 1, number 2, there's your SH group, your thiol, and there's your methyl group. And that's all there is to naming and drawing thiols. Two-chloro, 2-propane thiol. Okay. Again, working backwards, thiol group, which is an SH. Propane is 3 carbons. So 1, 2, 3. At number 2, there's a chlorine group. And at number 2, there's the thiol group. Two-chloro, 2-propane thiol. So there's your 3 carbons, an SH group, and a Cl group, both at number 2 position. Cyclopentane thiol. Cyclopentane is how many carbons?
5.
Pentane's 5 carbons. Cyclo means it's all connected in a circle. So 5 carbons. Okay, there's 5 carbons, 1 carbon in every corner. And there's a thiol group. Okay, we don't have to put number 1 because anytime we have a cyclical compound, the functional group is at number 1, no matter where I put it. By definition, the functional group is number 1. I could put cyclo 1 pentane thiol, but it'd be redundant, but I would not mark it wrong if you did that. Because technically it is at the number 1 position. But cyclo pentane thiol. Here we go. Again, it's at the number 1 carbon. You have a thiol group. Cyclo means cyclical, 5 carbons, all in a circle. Disulfide formation, the formation of a disulfide bond, which is sulfur connected to a sulfur. And that's important in a lot of our biological molecules. When we get into the chapters of biochemistry, with a lot of those connections that we're going to study. So the thiol disulfide redox pair, okay, reduction oxidation, controls a critical factor in protein structure called what's called a disulfide bridge. It's a reduction oxidation reaction that links two sulfides and forms the shape of certain proteins. Okay, so disulfide bridge is very important in biochemistry. Okay, so 2 cysteine molecules, which are amino acids, undergo oxidation to form cysteine. Okay, it forms a new bond and it's a disulfide bond in doing so. And here's the amino acids. And again, we'll go over this in chapter 17 or something like that as it comes up. Okay, you have here's 2 compounds, 2 separate molecules. You're going to have a reduction. You have an oxidation, means you either gain oxygen or lose hydrogen. Remember, oxidation is the gain of oxygen or the loss of hydrogen. Here we're going to lose a hydrogen from each end. That's oxidation. Okay, those 2 hydrogens are going to form here, and these sulfurs are going to link. And here's your disulfide bond. 2 sulfurs linked together. So you took 2 cysteine molecules, and through oxidation, with the formation of a disulfide bond, okay, we created cysteine. Okay, and it's reversible reaction. Going the other way is reduction. Remember, reduction is the loss of oxygen or the gaining of hydrogen. If we go backwards, we have gained hydrogen and broken this disulfide bond. Okay, so disulfide bonds are extremely important in biochemistry, and we'll be doing a lot of them. And all it is an oxidation reaction because you're taking a hydrogen off the SH group, okay, and then linking the 2 sulfurs together. That forms a disulfide bond. So if 2 cysteine molecules are in different protein chains, the disulfide bond between them forms a bridge, joining these 2 together. So it can form these amino acids into a chain. Okay? If 2 cysteines are in the same protein chain, it forms a loop. In other words, if you have a protein chain, looks like this here, and you have an SH sulfide bond here and a SH bond here, if you lose these hydrogen, if it's in the same chain, that disulfide bond now forms a loop in the protein instead of forming a longer chain. So it determines the shape of a lot of our proteins, and that determines their functionality in the body. I would write right in the way of the words here, huh? Example, disulfide bond is in the production and structure of protein called insulin. Okay, we make insulin, controls your blood sugar levels in the body. One of the final steps is the disulfide bond that forms to form the shape of insulin. Okay, if that doesn't form, insulin is non-functional. Okay. So insulin is initially produced as a protein called pre-proinsulin. Okay. Insulin is not released by the pancreas in the active form. Okay, it's released as pre-proinsulin, and then it's acted upon to form insulin. Enzymes remove 24 amino acids, and the formation of these disulfide bonds in the insulin between cysteine produces proinsulin. Okay, so once you form your bond, you chop off 24 amino acid N, you form the disulfide bonds, which loops around different structures, and it forms proinsulin. Proinsulin is still not active. You still have to activate the proinsulin into insulin. Okay, but disulfide bonds is one of the major components, is one of the major components of forming that compound, of forming insulin. Okay, so regions of the protein are identified as A, B, and C chains in insulin. The A and B chains are covalently bonded to one another by two disulfide bonds or bridges. Okay, the third disulfide bond produces a hairpin loop in the A chain of the molecule, so it loops itself around. Okay, the molecule is now ready for the final stage of insulin synthesis, in which the C chain is removed by the action of protein degrading enzyme like a proteases. Again, we'll get into all the proteases and where they break the bonds and how they break the bonds and all that good stuff too in the biochemistry portion. Okay? But you got to understand how the disulfide bridge form so we can break them apart and form actual insulin. So the active hormone is only 21 amino acids long. Okay, the 21 A chain is bonded to the 30 amino acid B chain by these two sulfide bonds. So we have 21 amino acids in the A chain and 30 in the B chain. So without the disulfide bonds, functional insulin molecules could not exist because there'd be no way to keep the two chains together in the proper shape. So once they bend around, those disulfide bonds form and it keeps the shape of the insulin molecule so it can absorb the blood sugar from the bloodstream. Okay. And there's what it looks like. That's what we're talking about. You have an A chain and you have a B chain. Okay. Disulfide bridges form a bond, link the A and the B chain, link the A and the B chain. Okay. That's pre-proinsulin. And pre-proinsulin, okay, goes to insulin. Okay. You can see that the disulfide bond is still there. Disulfide bond holds that together. And the disulfide bond links that. And now you have removal of this section right in here. And the disulfide bonds allow this to bridge and hold the chains together. Okay. You can see without the disulfide bonds forming, the A and the B chain would not stick together and you would not form the proper shape of insulin, and insulin would be non-functional. So disulfide bridges are extremely important in biochemistry. Okay. British anti-leucite called BAL is a dithiol used as an antidote in mercury poisoning. Okay. We don't see mercury poisoning too much anymore. I had a case of it, oh, holy cow, probably 15 years ago now. I had a elevator engineer, head of what's called Dover Elevator at the time. Okay, major company. He would go to work and he would be, let's see, how did it work out? He would do fine at work. And every weekend he would get sicker and sicker every weekend. And it turns out he had mercury poisoning. And what happened, he bought a coffee cup in Mexico and it wasn't glazed. And the mercury in the clay was being etched out by the acid in the coffee. So when he goes to work, he has regular coffee cups that were glazed and he was just fine. He'd stay home for the weekend and he'd drink out of the coffee cup at home he bought in Mexico, and it was etching out the mercury from the clay and giving him mercury poisoning. And he was getting extremely sick and they figured what was going on. And I was in the office and he had decay. I mean, this is a high-paid executive, and he had decay over most of the outside of his teeth from the mercury poisoning. So we finally figured out what was going on with that. But it's a dithiol is the antidote to mercury poisoning. Okay, it was originally developed an antidote to mustard gas. Okay, chemical warfare called leucite, developed near the end of World War I and was never used. Okay, it was banned by the Geneva Convention. By the onset of World War II, leucite was considered to be obsolete because of the discovery of what's called BAL, an effective, inexpensive antidote. So if you used it on people, they had the antidote. So it wasn't really used that much because we could combat it. Yeah. So two thiol groups of BAL form a water-soluble complex with mercury. Okay, if it's water-soluble, what happens? It can be absorbed out of the body in the bloodstream into the urine. Okay, so it's excreted from the body in the urine if we can make it water-soluble. Mercury is not water-soluble. Mercury is a heavy metal. It accumulates in the fat of your body and does not leave the body. Okay, When it's combined with these two thiol groups of BAL, they combine to it, they make the mercury now, this complex, this mercury BAL complex becomes water soluble. So it dissolves out of the fat tissues of your cell into the bloodstream and gets filtered out through the urine, which treats mercury poisoning. Okay, and this is the bluest lucite. This is BAL. This is a disulfide with an alcohol group on it. And that's what they used to combat mercury poisoning. Okay, and that's why the gas was never used, because we could combat it. All right, summary of this chapter. We have talked about alkenes being hydrated to form an alcohol. Okay, alkene, each side of the double bond, one gets OH, one gets H, we now have an alcohol. We get major minor products, we get 50 products, or we get one product formed when we do that. Carbonyl group. Carbonyl group is a carbon with a double bond. Reduction. Reduction means the adding of hydrogen or the loss of oxygen. So if we add hydrogen here, we get rid of that bond and we have an H and no H. Again, we formed an alcohol. Okay. So alcohol, oxidation of a primary alcohol gives you an aldehyde. Oxidation of a secondary alcohol, okay, gives you a ketone. Two arguments between the carbonyl group. Oxidation of a tertiary alcohol, no reaction. Remember, primary alcohol goes to an aldehyde, secondary alcohol goes to a ketone for oxidation, and a tertiary alcohol cannot oxidize. Because why?
Was it because lack of hydrogen?
Perfect, exactly right. There's no hydrogen on the carbonyl carbon. Okay, on the alcohol that has on the carbon that has the OH group, you have to have an alcohol, you have to have an H group for oxidation to occur, to form that double bond. Okay, if there's a carbon group here, if there's a carbon group here, if there's a carbon group here, there's no hydrogen on this carbon, so you cannot undergo oxidation. So I guarantee you'll see that on your midterm. Tertiary alcohols cannot undergo oxidation because there's no hydrogen on the carbon that has the OH group of the alcohol. So primary goes to aldehyde, secondary alcohols go to ketones, and tertiary alcohols do not oxidize. And then dehydration of an alcohol, when you remove the OH and the H, and you can form the alkene again, the double bond. Occurs with in a strong acid and heat. And this is going to form, dehydration will form a double bond again. Okay, those are the reactions we talked about in this chapter. That's our basic summary. So if you look at everything here, preparation of alcohols, hydration of alkenes will give you an alcohol. Reduction of an aldehyde or a ketone will give you an alcohol. Again, remember an aldehyde or ketone, they both have a carbonyl group. Okay. If we add hydrogen, which is reduction, adding hydrogen, we're going to add H to both sides. That will give us an alcohol. It will give us an OH group and then a carbon group. Again, if it's an aldehyde, it's going to go to, if it's an aldehyde, it'll go to a primary alcohol. Ketone will go to a secondary alcohol. Reactions of alcohol. That's how you make alcohols. Now, alcohols can react by dehydration. We can move water from them. Oxidation. We can add a carbonyl group to it. Okay. A primary alcohol oxidizes to an aldehyde. Secondary alcohol oxidizes to a ketone, and a tertiary alcohol does not oxidize. Why do my screen go black? Huh, that was interesting. All right, so the different reactions of alcohols. Okay, remember, this really helps a lot when we're doing our oxidation reactions with alcohols, if you remember that. Okay, dehydration synthesis of an ether. Okay, remember we took two alcohol groups, we took two alcohols and we did dehydration reaction. We moved OH from one, H from another, and we formed an ether. That's what we just started talking about that at the beginning class today. And here's a chart that summarizes all the reactions. So if you want to come back and review it, they're all right here. An alkene goes to an alcohol, an aldehyde goes to an alcohol. Alcohol could go to an alkene by dehydration. Okay, oxidation, are three types. You can form an aldehyde, you can form a ketone, you can form no reaction. And then these are dehydration synthesis of an ether, how to make an ether from alcohols.